Dr. Aditi Kathpalia, and you will have noticed that she's our only women speaker, but I'm very happy that we have a woman speaker after all. So Aditi did her PhD from NIAS under the guidance of Professor Nitin Nagaraj, whom you already heard today. And before that, she actually has a bachelor's degree from BHU, and she is a dual degree holder. She's the gold medalist of her batch. So she's a very good role model for all the students in the audience, especially girls. And she's working now as a researcher in the Department of Complex Systems, the Institute of Computer Science of the Czech Academy in the Czech Republic. What time is it for you, Aditi, now?
It's 1:30.
Okay, so it's not, yeah, it's a comfortable time at least. Okay, we are making, we are making you miss lunch, but that's okay.
I already had something. So.
You already had something. Okay. So her research interests, they actually include causal inference, causal machine learning, complex systems, information theory, and computational neuroscience, all of which make her eminently suitable to actually talk in a workshop on reservoir and computing and artificial neural networks. But the last time I met her, she also had another interest, which as it happens, somebody spoke about yesterday. I don't know if you were there for the talk, Aditi. Were you there for Jaideep Pathak's talk on climate science? Okay.
No, I missed it. Yeah, climate science too is an interest, or at least I have worked a bit on it.
Yeah, so so she has a variety of interests, and like our center does, namely it is a center for complex systems and dynamics. And one of the things which I'm really enjoying about this workshop is the way in which it's bringing engineering and science ideas, engineering, physics and mathematics ideas together in a not in a hodgepodge way, but in an organic whole. So having said that, let me hand over to Aditi. Aditi, can you start sharing the screen?
Yes. So thank you, ma'am, for that very nice introduction. And thank you so much for having me. So are you able to see my screen now? Sorry, I can't hear you. Are you able to see my screen?
Yes, ma'am. Yeah, we can see your screen.
Okay, great. So yeah, I will be speaking on causality and machine learning. And since ma'am already introduced me, I will go on to first of all thank my collaborators with whom I did this joint work. One of them is Dr. Nitin Nagaraj. You have already heard him. I did my PhD under his guidance. One is Hari Krishnan NB, who was also at NIAS and is now at BITS Goa. And some of the work was also done with Kirti, who is right now an undergraduate student at IIT Kharagpur, and she was working with me as an intern last year. So with that, I move on to the outline of my talk. So basically, what are the takeaways that you will have today from the talk are the following. So the first part of the talk is like an introduction, and it's an introduction to causality for machine learning. So the motivation behind it and what is happening in that area. And the second part is a completely different field, which is like causality estimation from time series data, which is like a complete field in itself. And then in the second part of the talk, I will be talking about giving some results that we have, and basically by using machine learning algorithms, and particularly neurochaos learning, which you have heard already about, and using that to check for generalized causal structure in time series, and then also to check if we can discover cause-effect relationships between system variables. So with that, okay, I start with something very basic. So if you think about what is it that machine learning does, right? So what it does is it takes in data that is given to it, and it also takes in the outputs for that data, and it gives us a program or a model. And then giving that model to the computer once again, and also our test data, we can get the test outputs. Right. So what machine learning is basically doing is that it is building statistical models and just predicting the label or output of our test data. So this is like the function of machine learning, and it assumes that all train and testing data is from the same distribution, like same probability distribution. And so whatever it does is basically by observing and then predicting, right? And this could be like observing sales of a particular product over time and predicting what would be the sales, let's say, next year, or observing like which of the emails are, for example, spam emails. And then if you get another new email, you could predict whether it is a spam email or it is not a spam email, and so on. So it basically observes and predicts. And if we look at it mathematically, what ML does is basically that it takes the inputs X and the labels Y, and which are thought to be observed as a result of random experiments. So any data that you are given are thought to be occurring as a result of a random experiment. And then what you do is that you wish to estimate, your ML algorithms wish to estimate what is the probability, conditional probability of the label Y given your input X by learning the joint distributions of X and Y, right? So if you already had the distribution with UP X, Y, then there's no problem. But since you only have the data, you need to sort of build an inverse statistical model and then compute this PY given X. And this learning is based on joint distributions, as I said, and then the assumption that these XI, YIs are IID, the data that you observed is independent and identically distributed wholes. So now, like, why do we need causal machine learning, right? Because there are some things that machine learning still can't do. And what are these things? So basically, it still cannot answer cause-effect questions. Like if I ask a question like, what would happen to my sales if we increase the advertisements, right, of the particular product? Then what would happen to the imports if we introduce strict policies? So, I mean, these are the kind of questions that, you know, you can see that they involve some kind of an intervention, a manipulation into the system. And this manipulation could be like a policy, like a treatment, like in case of giving medication to a particular patient, you can ask what would happen to the symptoms of the disease if you give that particular medication. So these itself may change the data generating process, right? And the data that you already have available from before is not under these kind of interventions. So your statistical model will not work in that case, or will give spurious results. So moving on with that, so if we look at it mathematically, what ML doesn't do, it doesn't tell us about this probability of Y given do X, that is a conditional probability of your label given something that you do to your input, right? And it does not utilize the data generating process or incorporate causal mechanisms behind your data. And also another important thing is that it is not able to generalize across different probability distributions, because a single causal mechanism or a single data generating process may lead to different joint distributions of X and Y. And if your machine learning algorithms learns from that single joint probability distribution, its predictions are not going to be correct in case of interventions in the system. And also sometimes this conditional probability, this P of Y given X may be independent of the joint probability of Y, X. And in fact, a single causal model sort of can result in multiple joint probabilities of like P of Y, X. So I mean, under these conditions, you cannot predict based on your statistical model. So, I mean, since ML can't do this, and if you still try to use ML to answer causal questions, or I mean, implicitly answer causal questions, not directly, but you want to predict something, and you still try to use ML, some really weird things can happen. Like, and so this slide basically shows what all can happen, like examples of what all can happen. And one of them is that there was this this ML algorithm in the US, which was used to determine how much sentence should be given to the criminals, like how long they should be imprisoned for, was flagged racially biased. And what it was doing was that it was correlating the fact that if you are a black, you would commit more crimes. So if you want to give this particular subject some like sentence based on what is the probability that this person will reoffend in the near future, you may give a more strict sort of a sentence to a black person rather than a white person, and which was particularly not correct, because it was just correlating the color of the skin with more crimes and doing that. And then there could be something like there was this again a popular science article published that chocolate could make you more intelligent. This was because there was this study published which claimed that chocolate consumption would enhance cognitive function, because there was a correlation between the amount of chocolate that was consumed in some countries and also the number of Nobel Prize winners in those countries. So I mean, so these kind of results, and then you could just go on, like there was another article saying that relaxing makes you die. So it's kind of both funny and also very what kind of word I should use? It's very extreme that you can make such kind of conclusions based on just correlation and implicitly implying that there is some kind of a causal effect between two events. So this gets us to the heart of the matter, that correlation is not causation. And most of your machine learning algorithms, since they are looking at the joint associations or correlations of your input and your label, are actually doing that. And I will explain this by taking a simple example that correlation is not causation. So if you look at your sales of fan and the consumption of ice creams in a particular region, right? It is quite often that in summer, both of these will go up. But definitely there is no direct causality from the sale of fans to the consumption of ice creams or the other way around. It is basically the weather or the temperature in that region that sort of causes the two to go up. So it's not that if two things are correlated, they will also be causally related. So to make causal inferences based on such kind of correlation can be really problematic. And if we look at two correlated variables, X and Y, what are the causal possibilities of their relation, it could be that X causes Y or Y causes X, or there is a common confounder like a Z, which is a cause of both X and Y. So, I mean, in this case, I ignore the bidirectional effects, and I'm showing what are the possibilities if we look at only one-way causation between the variables. So with that, we also, like it's not just that correlation is not causation, but within causation itself, you can have several levels. And these levels are given by Julia Pearl, who talks about, how can we bring machines closer to human-like intelligence? And one of the ways he says is that by incorporating causal learning abilities in them, because humans work based on, inferring causality based on reasoning and so on. So, and like, if you look at the different levels of causal understanding that we have as humans, we can classify them onto like 3 levels. So the most rudimentary or the basic level is what we call as associational causality, so which involves associating events with possible causes by seeing, observing, or correlating. And an example for that is, if you just look at which symptom and disease occur together, you can say that whenever this disease occurs, these symptoms occur, so it is probably that this disease causes these symptoms, right? And then the second level is interventional causality, in which you actually do something to the system, as I was referring to before. You do something to the system, like make a change, actively experiment on that system to observe what is the effect of that intervention. So for example, if you are sick and you have fever, and you take in a paracetamol and observe its effect on fever, then this is a kind of intervention that you do on the system to see what happens, what is the effect of that. Then the third level is counterfactual causality, which is the highermost level of on this ladder of causation, and it involves your brain. So basically you need to imagine and you need to retrospect to make causal inferences. So go back in time and think, what was it that caused the present? In the sense that if you had fever and your fever got cured at a later time in the future, then in the future you would think that, oh, was it that paracetamol that cured my fever, or maybe was it like a herbal tea that I had that cured my fever? Right? So this ability of going back and retrospecting to make causal inferences. So that's the third level. So this is very important in this field of causal machine learning. And this has been used as a basis to a lot of sort of design methods which could do causal inference. So with that, I move on to this do operator, which I briefly referred to before. So how can you have something in statistics which looks at what happens to the system when you do something? So they develop this do operator in which they want to look at what is the probability of your label or your output y given do of x equal to x1. That is, you set your inputs equal to a particular value x1. So now what is the difference between this y x is equal to x1 and this do x is equal to x1? So the first is the probability of y being true given the observation that x is equal to x1. And then the second, the do operator, gives you the probability that y is true given that an intervention is made that sets x to x1. So you do something and then x goes to x1. And in general, these two are not equal. And I can explain this by taking the example of a barometer where you observe what is the reading in the barometer and use it to predict rain, right? So you say that if the probability of rain given that the barometer reading is high is sort of greater than the probability of rain given that the barometer reading is low, because it is pressure which sort of affects both pressure in the atmosphere, which sort of affects both rain as well as the barometer. But what if you do something with your barometer? You hack it too high, you hack it too low. That really does not predict your rain, right? So there's no change in the probability of rain given your barometer was hacked to any particular value. So there's a huge difference between this, what happens as it is in the environment, your data without doing anything on the system, but with doing, and also with doing anything in the system. So there's a huge difference between the two. So now with the do operator, let's move to how do you give a solution to your interventional queries. So you could do one thing, which is that you could take data from randomized control trials. So if you have heard of randomized control trials, what happens is that you have some system where you want to study the effect of something on something, and then you can have a control group and a group on which you give some intervention. So for example, if you want to look at the effect of a drug, you have a control group to which you give placebo, and then you have another group to which you give the actual medication. So that's, you directly take data from that. But what happens if you can't? For example, in the case of smoking and lung cancer, if you want to look at whether smoking causes lung cancer or not, you cannot really force a person to start smoking just because you want to conduct your experiment, right? So in that case, what they say that you can do is that you can start to use what are called as structural causal models, in which you assume certain equations for your data, and also you assume like a causal graph for the data. I'm just giving you this as an example, that if you have XYZ variables and they have some functions, then I mean, this is how you can have the function and you also have the data. And then at the same time, what you can do is you can also do something with these equations, that you can force some variables to become what you want them to become. So in this case, for example, I would want to do y to equal to 2. So I want to set the value of y equal to 2. And you have this and you have your data, and then you could actually solve for these models. And of course, there are a lot of assumptions here. But I mean, this is just to get an idea. I won't get into the details of how they are solved, and there's a lot of research happening in it. But I'm just referring to it to show you the difference between these kind of causal models and statistical models. So basically, your older machine learning problem was saying that if you have your data, the circle on the rightmost side of the slide, this XYZ data, you could use it to infer your statistical model, which is the probability of XYZ. But now we are saying that we could use that data to infer our causal model. But I mean, this causal model has a lot of assumptions that you need. You need to know the basic structure of how one thing affects the other. But at the same time, it could be more informative and useful if you want to predict certain things. So there are two levels here. One is that you have your data, which is, finite. So anyway, it is difficult to model the probability distributions, which you would be doing in the statistical model. But here, it's not only that problem, but also the problem that you have to, you can have multiple probability distributions given your causal model. So there's a lot of problems, but at the same time, it can be useful. And so you want to do it. So with that introduction, I move on to now causality estimation from time series, which is the field which I've been mainly working in from the last few years. And looking at, as I said before, this is a complete field in itself. So there's no machine learning here at the moment. And what you want to look at is that you want to infer the causality of given time series data from a particular system. It could be the brain. For example, you could have recordings from different EEG electrodes, and you want to see how the different regions of the brain functionally sort of cause each other. How is the information flow happening in the brain? So for these kind of questions, you could use this. Then it has been used also in econometrics, where you want to look at, for example, the cause-effect relationship between stock prices and trading volume. In climatology, where you want to look at the relationship between, for example, greenhouse gases and temperature. So, it has been used in all these areas. And this brings me to the mathematical formulation for causality, which was, given the first time by Wiener, who said that given time series data, how can you check whether a time series Y causes a time series X? So he said that if the past values of Y contain information that help predict X above and beyond the information contained in the past values of X alone, then Y causes X. So there's something more to the past values of Y that helps to predict X above and beyond its own, the information contained in its own past, right? So that was Wiener's idea. And then this was, put into equations by Granger, who formulated the concept of Granger causality. And he put it in terms of linear regression modeling, and he used what are called as autoregressive models. So we heard about these VAR or AR processes in Professor Eric Bolt's talk yesterday. And so what Granger did was he said that now, given our time series X, and if you want to look at the effect of Y on X, this X can be modeled in two ways. One is by this model 2, where X is caused only by its own past. So you have these terms xt minus tau, and then you have also an error term there. But then the first model is that you have your x being caused by its own past values, these xt minus taus, but also by the past of y. So yt minus taus are there, and the error term. So now you look at which of these models is better. And the way you could do it is by looking at the variance of the error terms in the two models. And he said that if the variance in the error term of the model in which x is caused only by its own past is sort of higher, then that's a worse model. And so this term would actually, this log term would actually be greater than 0, and y would be causing x. So this epsilon c is actually lower. And so this magnitude of f could be used to quantify the degree of dependence. So this is one of the methods, and there are several other data-driven methods. So we can call this a data-driven method because the model being fit to the data is actually very generic, and it holds true for many of the real-world data that we sort of observe. And this method, as well as some other data-driven methods, have some problems, as you can see. One is that they also fall on the rung of associational causality that we discussed before, because we are just looking at the correlations of the past values of y to the present values of x. And they also require some other conditions, that your time series should be stationary. And I mean, if you have missing data, you have a lot of noise in the data. If you have short-lived data, these methods fail. So what we did was we introduced a new measure. It's called compression complexity causality, that I worked on in my PhD. And to introduce that, I introduced this concept of dynamical complexity before. So what this dynamical complexity captures is how a past of a time series influences its present state. So if you have a time series x, say x1 to xn, as you can see on the right-hand side of the slide here, you can divide it into windows. Like you can have a past window called x, and you have a present window delta x. And then you can look at what is the change in the complexity when we consider the entire x plus delta x together and only the past x. So that's the dynamical complexity. And you can estimate these complexities using a measure of compression complexity, which is called as effort to compress, and it literally measures what it is the effort required to compress your given data. And these estimators are based on lossless data compression algorithms. So with that, moving to this compression complexity causality. So we have already seen that, you know, we can capture the dynamical complexity of your delta x, that is a new window of time series given your past window x. But what you can also do is that you can do some kind of a surgical intervention, what we call in the system, and we can create a new hypothetical time series. What if your y also evolved to delta x? And now you can look at what is the change in the dynamical complexity when only x evolved to delta x and when both x and y together evolve to delta x. So in that sense, this measure is a measure of interventional causality, but of course, this will also hold only under certain cases, because like you cannot do any kind of intervention you want, but you are just doing something hypothetical to see what happens to the system. So once again, this CCC is estimated in line with the Vienna's idea I just told you, and it is seen to be free from the assumptions of long-term stationarity, and it is robust to short-length data, missing samples, low-resolution data, and so on. And it has been applied already in several scenarios in neuroscience, in climate science, in studying the behavior of musical instruments. So already it has seen a lot of applications. And if we look at where this particular method stands on the ladder of causation, I mean, if we can sort of adapt the ladder of causation also to this field of time series causal inference, then this compression complexity causality, even though it is like a data-driven measure, it will still fall on this rung of interventional causality, unlike other data-driven methods like Granger causality and transfer entropy, which fall on the associational rung of causality. And then other methods which fall on the interventional rung are model-based methods like the structural causal modeling that I referred to before, and there are other methods like dynamical causal modeling. and so on, because like they would assume certain equations for the data, and then you can give some kind of interventions to the model, in the sense that you could give some hypothetical inputs to the model and see what happens to the data. So with that, I mean, this was an introduction to time series causality. And now what is, I mean, happening in this field of time series causality and ML, right? Where do the two meet? So it's like one of the problems that people are trying to solve is that of causal treatment effect estimation. So you want to impact the treatment or intervention of, estimate the impact of treatment or intervention over time. So if you, for example, want to predict a patient's response to a drug over time, like you have a single time series in that sense, that you will have patient's response, like any parameter, for example, heart rate or respiratory rate or whatever. I'm just giving an example, that this is how it changes over a period of time. And then you want to see if your treatment that you're giving to the patient is actually working. Or it could be an effect of government initiative on cigarette sales, for example. So there's a policy which has been, which came into place some time ago, and you want to see how well it is working. Like, is it reducing the sale of cigarettes, or yeah, whatever you want to happen. So you could predict that. So now the other area in which people are doing research is this, looking at this causal relationship between time series. What basically all these causal inference methods that I just discussed for time series can also do, that you want to infer what are the dynamical connections between like dynamical sort of what we call as functional connectivity in your network. So they're also looking at that. And since these causality methods can already do something on the, to infer that, people are exploring the combination of ML with these causality measures like grandeur causality in order to improve these methods. So this is basically to understand like coupled systems or synchronizing systems, or systems in which there is some kind of information flow. So with that, I mean, I now move on to what results we have for using machine learning, and particularly neuro-chaos learning, for some of these kind of tasks that I talked about, like learning generalized causal structure and time series, and learning cause-effect relationships between system variables. And I mean, the tasks that I will be showing here are not that difficult. They can be solved by other statistical means. It's just to see whether our algorithms, like conventional machine learning as well as this neuro-chaos learning that we have, can actually sort of work for, in case of, you know, sort of causal processes. Can it have any kind of causal understanding for the data that we are giving to it? So how do we do that? So first of all, what we did was that we wanted to learn whether there is any causal structure in time series that we are giving to our ML algorithm. So, I mean, basically, causal structure is that your past values in the time series are affecting the present values. And I mean, this is also going one step before doing an intervention on that system. So is it that they can only detect whether there is an influence of past to the present without any intervention from outside at the moment? And this is basically to ensure that, you know, your algorithms sort of make sense of ordered data. So with that, we simulated some time series, like causal time series, which came from these autoregressive model AR, which I just mentioned in case of grandeur causality before. So your present time value of X is basically like a sum of this a tau xt minus tau, so some coefficient multiplied by the past time values of X and some error term. So, and that was a causal model. And then the non-causal time series was, you basically just take time series values which are drawn from some probability distribution and are independent and identically distributed. So you could choose like Gaussian random process, or you could choose uniform random process, and then form your time series from that. We did that, and we had the following train and test data sets. So we have like the AR train and testing set, in which The non-causal time series were generated from uniform random distribution with standard deviation 0.01, mean 0, and then the causal time series were these AR processes, and the train test ratio was kept to be 70 to like 30 for the entire data set. And then we had these distribution shift testing sets. So from what I said before was that, I mean, if something is learning sort of a causal mechanism, it should be free from the distribution of the data. So what if we give like causal time series as before to the data, like the AR training data? So the causal time series still remains the same in the testing set 1, but we give a different kind of non-causal time series, which is drawn from a different distribution. Like, let's say the standard deviation of the random Gaussian process becomes 0.09. So that's one kind of distribution shifting. Then another distribution shifting test was given, in which we gave a completely different non-causal time series to the data, which was drawn from like uniform distribution. So the causal time series remained the same as for the AR training and testing set. So the causal is AR in each case, and the non-causal time series is sort of changing. So with that, we used these methods like logistic regression and long short-term memory processes to classify between causal and non-causal time series. And we used the time series values directly, and we used, I mean, that was one case when we used the time series values of our AR and whatever random processes directly. Then the second case was where we transformed these signals to the Fourier domain, and we gave the Fourier amplitude of the signals to these classifiers. And then the third case was where we extracted ChaosFEX features. So you have already heard about neurochaos learning, in which you can extract these features from the chaotic firing of neurons. And so this is what you already saw. So in this case, you basically give your each time point to each neuron in your neurochaos learning architecture, and then you the neurons fire until they reach the value of the stimulus. So that particular time point in your time series basically, and they were started from some initial condition Q, and then this trajectory can have several features, and then it can be used to get the ChaosFEX features. So we use this ChaosFEX plus ML scheme because the ML algorithms that we used are logistic regression and the LSTM, because that works. LSTM is supposed to work for sequential time series data. So what kind of results do we get? So when we use the time series values directly, you observe that our accuracy for the training set, like if you just take the AR training set, it was high, of course, because that's the data you have been trained on for both LR and LSTM. And if you take the AR testing set, so it also contains the same kind of distribution, but still you see that for time series values model, it was not able to work. I mean, neither LSTM nor logistic regression was able to give good accuracy for this kind of data, I mean, which came from the same distribution as your training set. So what they are doing is basically classifying your causal and non-causal time series, right? So that is, so the accuracy and the F1 score shown up for that. And then if you move to the second of model where you extract frequency domain features from your data, like you just take the amplitude of the Fourier domain and feed it to your classifiers LR and LSTM, you see good accuracy even for the AR testing set, but still you cannot see good accuracy for your distribution shift testing sets where you had a different kind of a non-causal process. So this means that definitely these algorithms are not able to have like a causal understanding even when frequency domain data is given to them, like frequency domain amplitude of the signals is given to them, because they're not able to work for these kind of distribution shift data. Then we use the ChaosFEX features model. And in this case, we gave like the AR training set, AR testing set, all the 2 distribution shift testing sets, and still we could get like very high accuracy, like 100% accuracy. And then we thought we would try for other distribution shift testing sets. Like, what if now my causal time series also changed and not just my non-causal time series? So we took autoregressive processes with a very high order, like a long-term memory. Then we took autoregressive moving average processes, and we took autoregressive fractionally integrated moving average processes. So these are also long-term processes. And we looked at how the chaos FEX features model behaves, and we got like very good accuracy for all the cases, as you can see from the rightmost column of this table. So, I mean, at least neurochaos learning by using chaos FEX feature extraction was able to learn something about the causal structure in that data, because it was able to distinguish between completely random time series and time series with some kind of causal structure. And the causal structure could be of, you know, very, I mean, it was hoped that it was learning a very generic causal structure, because it was trained on just our data and then tested on ARMA and RFIMA and so on. So moving on to the second part of the results, where we wanted to look at cause-effect relationship between system variables. So this is something you just say that, you know, your X time series is causal, while your Y is the effect of this particular X time series. So now the cause-effect classification task in this case was that can your existing ML algorithms help in this cause-effect classification? So your X and Y that I talked about in the time series causality introduction, that can you classify whether one time series is a cause and the second is an effect? And does this success in cause-effect classification imply that there is a preservation of causality? So can you be sure that, you know, if there's you know, cause-effect classification happening correctly, there's also a preservation of causality in the feature space of that model? And then the last is transfer learning. So was there enough generalization in learning the causal structure that, you know, you could also learn the cause-effect relationship for a different pair of time series? So we will look at all of these in this part. Just a second. So looking at the methods that were used, so one of them was this ChaosNet with 4 different chaos FEX features, which were discussed in Dr. Nitin's talk earlier. Then we had this 5-layer deep neural network, and then 1D convolutional neural network, and LSTM. So we coupled tent map processes, this MT and ST. So as you can see, so this black one shows the return map of the master, and the red one shows the return map of the slave in the figure on the left-hand side below. And so this was generated, and then the train test ratio was kept to be 80:20. And with this, we look at the results of classification and preservation of this cause-effect relationship. So how did the different machine learning algorithms, including neurochaos learning, work to classify this MT and ST time series? So the master time series of the coupled tent map system and the slave time series of the coupled tent map system. And we see that from this figure, like on the top, that ChaosNet as well as deep learning both work quite well for classification, especially in the range. So basically at 0 coupling, so the x-axis shows the coupling coefficient between the time series. At 0 coupling, there is no causal interaction, so the F1 score should be poor, like around 0.5, as can be seen for ChaosNet and DL in this figure. And then when the coupling increases between the time series, there should be the correct classification of cause and effect. And then once the time series synchronize beyond, let's say, coupling coefficient of 0.6, then the F1 score should once again start to reduce, because then your model should not be able to classify the cause and effect. So we saw that the the behavior of ChaosNet and DL was quite good, but the other algorithms did not show good behavior for classification. So we wanted to check, is it actually that, that there's a preservation of causality in the feature space of both ChaosNet and DL, and also we could check the other algorithms that we have here, that it is working well sort of to classify the cause and effect. So how could we do that, checking whether there's a preservation of cause effect in the feature space? So what we did was we used the conventional time series causality methods like the GC or CCC. So in this case, we use compression complexity causality, CCC, to check whether there was, the feature space of the two time series like S and M that I mentioned before was actually, that causality was still preserved in the feature space. So we see on the left-hand side below that the original causality between the time series X and Y is like, if you look at M to S causality, it's shown by the red curve here. So there's no causality really, but because the values are closer to 0. But if you take causality from M to S, there should be an increase in causality with increase in coupling, and then it should begin to decrease as the coupling coefficient becomes larger because there's synchronization. So so the values here are sort of negative, and negative CCC is possible, and that's a different story. But now let's look at the chaos FEX features. Was the same trend visible? And it seemed to be visible, because then if you look at S to M causality, it was much lower in magnitude than the M to S causality, which increased with increased in coupling. So there was a preservation of causality in the feature space. And then moving on to whether there was a preservation in causality using DL, LSTM, CNN, we saw that that was not the case, because we could not see that there is an increase in the causality in the feature space for these methods with an increase in coupling. So with that, moving on to transfer learning. So can we say that if we train our model on a particular kind of tent map processes, will they be sort of able to classify another kind of tent map, coupled tent map processes, like with, let's say, with a different skew parameter like B1 and B2? Or would they be able to classify coupled logistic maps, for example, just by training on the tent map? And it seemed to be the case that they were able to classify, at least for a long range, where the causality should hold, in the sense that between 0.1 to 0.6 and so on. Both ChaosNet as well as DL could do the classification, but as you have seen that DL was not able to preserve causality in the feature space. So we were not sure whether it was doing a causally informed classification. So now ending sort of with my last result, which is more very sort of open-ended, because I started exploring this. So what happens to reservoir computing if you want to classify causal and non-causal time series, like a random time series? So what I saw is that reservoir computing also works pretty well in this case. And when I want to do cause effect classification, the second task that I talked about, it is that we get sort of 100% accuracy even with reservoir computing, but not just for this range of coupling where the tent maps are not synchronized, or where there's no coupling, but for all the values of coupling. And this happens, as you can see with the black curve here, with a lot of data, this happens. The accuracy or F1 score sort of goes down for the case of zero coupling when there are less samples to train the reservoir computing network on. So it seems to me that maybe the reservoir computing architecture is learning more than the cause effect relationship. Maybe it's also learning the B1, B2 parameters of the data. And the NVAR equivalence that Dr. Bolt talked about yesterday seems to suggest that. So it is possible that, you could actually use reservoir computing for inferring your causal connections and for doing cause effect classification, but we want to look into it more deeply. And so with that, I conclude my talk, and hopefully I have convinced you that ML algorithms need to incorporate causal understanding to move towards human-like intelligence. And then what we have done is we have proposed this compression complexity causality, which is an interventional robust measure for time series causal inference. And then we have also explored conventional ML algorithms as well as neurochaos learning for performance in causal tasks. And right now, very simple causal tasks like whether they are able to identify causal structure in time series, do cause effect classification, do transfer learning of causal structures. And it seems that NL works pretty well in all of these cases. And for future directions, I think looking at the talks in this workshop, maybe we can say that, we could use like RC and NL on time series and dynamical systems, and they seem to perform pretty well. So also, can we bring in the dimension of causality? And there's some work already happening with RC on inferring network links and so on. So can anything be done on the intersection of these three and to develop more sophisticated causal learning algorithms? And can we combine these NL-RC architectures with time series causal inference methods that I talked about? And can they be used for predicting future causation and extreme events? So yeah, these are some open-ended questions that we can think about. And with that, I would like to end and acknowledge my current supervisor here, Dr. Milan Palash, and the funding agencies, and also advertise for a postdoctoral position here where we want to use machine learning and causal inference for prediction of extreme climate events. So if you are interested, you can write to Professor Milan Palash. And thank you so much for listening. And if there are any questions, yeah.
Thank you, Aditi. Yeah, go on. Was there a question?
Stop sharing.
Was there a question?
Mademoiselle, monsieur, dans quelques instants, notre TGV desservira la gare de Mâcon-Locher TGV. Prochain arrêt, Mâcon-Locher TGV. Avant de descendre, assurez-vous de ne rien oublier à votre place. Nous vous souhaitons une bonne journée. Prochain arrêt, Mâcon-Locher TGV. Segnali, arriviamo subito alla stazione.
Hello.
Dr. Hinod.
Sorry, I could not hear what he said. Did he say something?
Maybe you could type the question.
Okay.
Oh, okay. Anybody else? I have a question, Aditi.
Sure.
This in this context, does it make any sense to think of inverse problems?
I mean, this causal inference is a kind of an inverse problem, but you also have some assumptions to begin with. But are you talking about the general structural causal model framework or time series, or?
You could explain in any context.
Yeah, so I mean, if you think about the structural causal models, it is actually about solving like an inverse problem where you have the data and you also have sort of like an assumed model, but you don't know, for example, many parameters of that model, and the parameters are the links, the strengths of the links between your variables. So there you could use this to like structural causal modeling to infer the strength of the links. But if you think about it in terms of a time series problem, then there are several model-based methods where this is treated as like an inverse problem where you actually figure out what are the strengths of your connections. For example, if you want to look at brain connectivity, there is dynamical causal modeling and you could infer the strengths of the connections. But I think one interesting thing would be to do is to combine both, like your model-free methods like Granger causality or compressional complexity causality, and the other methods to do this kind of inverse.
Do people try to use these things in this context, or I mean, have there been any attempts like this?
I think the combination part, I have not seen much work at all, but standalone, if you look at the model-based methods for doing causal inference, yeah, there's, I mean, a lot of work in that area, including the structural causal models, something called as dynamic causal modeling. And I'm sure there might be other methods as well.
Yeah. Any other questions?
I had a quick question. So I don't entirely follow exactly how CCC is defined, but you were saying something about how CCC ends up being better than something like Granger causality or transfer entropy because it can work all right even when your data is like shorter time series and things like that. Can you just give some intuition about why CCC ends up working even though these other methods fail? I thought it would face like a similar problem.
Right. Yeah. I mean, so one of the things is that it does not need like long time series data because it does not build sort of probability distributions based on the data. So if you look at transfer entropy, right, you have to build your transition probability matrix. If you look at Granger causality, you need to compute your correlations, like lagged correlations in the time series. So you need a lot of data. But what compression complexity causality does is that it uses data compression algorithms. So because of using that, you actually look at some patterns in the data and how they are changing and what is your ability to compress those patterns. And it can work with really short lengths of data. And then there's also like, I mean, you need not worry about the fact that there are missing samples because you take blocks of data. So even if like 1 or 2 samples are missing, it sort of works well. Not 1 or 2, but in fact, we have shown that even for a large percentage of missing samples, it works well.
I see. So I think I understand better why my confusion was then, because I think, so what kind of data compression models are you using? Because my understanding of usually when you're trying to do lossless compression, often your lossless compression algorithm depends on the distribution of your data. So I kind of thought that you would need to be able to have some estimate of the distribution before you can do the compression part.
Not really, because so first of all, we don't really use lossless data compression methods for compressing. So there are some methods which estimate complexity of the data before you would compress them.
I see.
So how let's say how much structure your data has or how random it is, that these kind of methods can sort of infer, and this kind of I mean, if you have heard of Lempelsive complexity, or there are also other methods, and this effort to compress complexity that I talked about. So it's basically looking at patterns in the data, and yeah, I think Dr. Nitin can add something more to this.
Yeah, Sarthak, I mean, so the intuition what you're saying is right in terms of one class of algorithms which build a statistical model for the data. But then there are these dictionary-based methods like Lempelsive and other substitution-based methods which don't build a statistical model. And there are theorems which show that the two actually converge, in terms of optimality. So you dictionary-based methods implicitly learn the PDF. I mean, they don't explicitly build a statistical model actually. So
I see.
Yeah. Grammar-based methods like context-free grammar or context-based grammar. So those methods don't build a statistical model explicitly.
Okay. Yeah. Thanks.
Yeah. So we have 1 minute before we switch to Sarthak. So there's room for one last question. Anybody? Okay, so I would like to thank Aditi for a very nice, very clear talk. because I don't think causality is so easy to explain. And I think she did a very admirable job of exposition. Aditi, I hope you'll be able to share the slides with us so that we can look at things. Yeah, so that we can look at things at greater leisure. So we hope
Thank you so much, ma'am.
yeah, we hope you'll be